Hi, in this video I'm going to be explaining exercise 11. The topic is arithmetics. Okay, let's continue. I'm going to put okay, first I want you to subscribe because I'm going to be uploading more videos and you want to stay updated. Okay, next, if you want to help me, give me a marker. You can find me in Int1, or this is my Facebook account. So marker, I'm using this marker right now. I want marker like this and different color, like I need black and red. Blue is okay as well. So yeah, this is just in case. Next, before I start, I want to review this one. So if you have this A more than B, it means that n divides A minus B. So it's just like division, but like writing is in a more advanced notations, because we are in, it's just like, you know, division. Because we're doing bachelor's degree, it's just more with advanced notations. We're learning this one. It's easier than Taylor expansion, believe me, because if you have this one, you can multiply it by C, and you can have AC is equal to this AC is equal to more than BC. If you have this one, you can calculate the power to the K. And if you have this one, it just works like equation for plus, minus, and multiplication, but not for division. Important. I want you to learn this first. And next, the first problem. So in the first problem, we have p prime number, and then we need to prove that 2 divides p minus 1, and then 2 divides p minus 1, and then okay, and then 2 divides p plus 1. Okay, in this case, first you write, we know that p is what? Prime. P is prime. And we also know that p is not equal to 2. Why? Because it's given here. P is more than or equal to 5. So based on this, we can have 2. This divides p, but if you do like this, 2 doesn't divide p. So you can write p as, if you divide p by 2, right, p mod 2 is equal to 1, right? And according to the properties that I just showed you, you can subtract minus 1, and then you can add 1. If you subtract minus 1, you will have p minus 1 mod 2 equals 0. And if you add 1 for both sides, you have p plus 1 mod 2 is what? 2. Or it means that because it's 2, you divide 2 by 2, remainder is 0. So like in here, it means that you divide b by 2 and the remainder is 1. For example, this is just example, 12 mod 5 is, what is it? 2, because you divide 12 by 5 and remainder is 2. Here you write remainder, is how it works. And so because of this and this, you can decide that conclusion, 2 divides p minus 1 and 2 divides p plus 1. Also let's say for all, this is the end, but here for all k which is integer, you can say p is equal to 2k plus 1. No, it's not for all. Oh, maybe for all. Yeah, k here, k must be what is it? K must be integer, and that's why it's this. So p can be written by 2k plus 1, because p is not 2 and p is more than or equal to 5. If we have this one, let's say, and then p minus 1 is going to be, p minus 1 is gonna be equal to 2k plus 1 minus 1, which is 2k. It means that 2 divides p minus 1. If you calculate p plus 1 is equal to 2k plus 1 plus 1. It means that it's equal to 2 goes out, then k plus 1. 2 divides p plus 1. We'll use this in the next problem. Okay, number 1 is done. Next page. So we want to deduce, in the second, we want to deduce 8 divides p square minus 1. And p is of course more than p is of course more than 5. And next we have p square minus 1 is equal to p minus 1 and p plus 1. Agree? Okay, next. Next, because I have this one, I can continue based on this. Look, I can continue based on this. I'm continuing based on no, not based on this. Like based on this line, like this line and this line, this one and this one. I'm continuing. Instead of p minus 1, I'm writing 2k. I mean, I wrote it here. I don't want to rewrite it again. 2k, and then instead of p plus 1, you can write 2 times k plus 1. What I did is I just inserted this one and then this one, and in here I continue. It's equal to 4 times k plus 1. Right now, in my mind, from this I know that 4 divides p square minus 1, but my goal is not 4. I need to have 8 here. That's why I continue. I need to focus on this one. If I prove that this 2 divides this, then that's it. I can get 8. So now this was the first step, and second step is I focus on this. I take k plus 1. My goal is I want to prove that 2 divides this. And now imagine k is integer, right? K is integer in our case. Let me mention here. K is integer. And 2.1, case 1. Case 1. Case 1 is, let's say, k, you divide k by 2, mod 2 is 0. It means that it's this, and then what is it, case 2, 2.2, case 2. You divide k by 2 and it's 1. Do we have the third case? Why am I using mod 2? Because I want to prove that this one divides 2 divides this one, because I want to have 8. 4 times 2. That's why I'm using 2 here. But do I have any other case? No, because if you divide a number by 2, you can only have 2 remainders, 0 and 1, and that's it. And so in this case we know, based on this, we know that there, for all, there we can find a natural number where let me see, you can see it, k is equal to 2a, right? If k is equal to 2a, then p square minus 1 is 4 times k plus 1, which is, what is it? Oh no, wait, let me just wait a second, please. I want to take all these papers, like here. I forgot. I'm sorry, I can't make another new video. No time. I'm gonna put the papers here and we continue here. Okay, I just remembered this. My bad. And then here, look, in here, k is equal to 2a, and k plus 1 is 2a plus 1. And it means that it's 8 times a 2a plus 1. From this you can say that 8 divides p square minus 1. You stop here because we have 8 here, because of this and this. And now case 2, if we have this one, you can say for a is natural number, k can be written by 2a plus 1. It means k is odd number. Okay, and now p square similarly, then p square minus 1 is equal to 4 times k minus 1, k plus 1, and I'm getting this one from here, and I continue. 4 times k is 2a plus 1, and 2a plus 1 plus 1, and in here 2 goes out and it will be 8 times 2a plus 1, and this one will be a plus 1. From this we can decide that 8 divides p square minus 1, and based on case 1 and based on case 2 we can conclude that 8 divides p square minus 1. Okay, this is done. Next. Third, we have this. We need to prove this. We have A divides B or A divides C, and we need to prove that A divides B, C. Okay, in order to prove this, in order to prove that this, we need two cases. Case 1, because we have OR, we take first A divides B. Let's say A divides B, and then what did I no, it's not OR, sorry. What? OR? Oh, okay, it's OR. So we first take this one, and then yes, it's OR. I was just reading the question. Oh, let me read the question. Now wait a bit, please. Okay, now it's OR. We need to prove this one. And case 1, we have case 1. We take, this is case 1, this is case 2. In case 1, if we have this one, we know that there exists k, which is integer number. Okay, it's recording. Okay, k is integer number, and b is equal to k times a, right? B is equal to k times a. Then we can write, we take this BC can be written by KA times C, and this is equal to A times KC. From this, you can decide that A divides BC. Okay, now number 2. Similarly, we have case 2. We take A divides C because it's OR here. If A divides C, again there exists K, which is integer. C is equal to KA. Then BC is equal to B times KA. This is equal to A times BK. This means that A divides BC. Based on case 1 and case 2, we can conclude that A divides BC. Okay, that's it. Next. Number 4. We have 3, and we need to prove that 3 divides p square minus 1, and p is more than this. Okay, now prove. So before I start, I need to give you the main idea. So we have different cases here. Imagine p is integer prime number, right? If p is let's just say p is integer. You can have p is integer already. It's prime integer, same. And if you divide, you calculate mods 3 mods 3 mods 3. Why? Because of this. If it was 4, we would calculate 4 for 4 here. P mod 3, it can be 0, the remainder can be 1, the remainder can be 2, remainder can be 3. No, it's just the same like this. So you can only have 3 remainders. Okay, now we have these cases, and now we don't have to take care of this case because p is prime, right? P is prime number. If this means that p is divisible, 3 divides p, it means it's impossible because p is prime. So we don't need to, so we only need 2 cases. So case 1, let's say p mod 3 is 1. In this case, according to the properties I showed you, we can subtract minus 1, and then we can add plus 1. So if you subtract minus 1, it's p minus 1 here, and this 1 minus 1 is 0, and this, and then p plus 1 is 1 plus 1 is 2, 3. I'm just adding p1 for both sides, 1 in here and in here. Okay, I have this one, and according to this, p minus 1, p plus 1, is equal to kind of mod. So you can multiply this one according to the property. 0 multiply 2 mod 3, right? And it means that it's mod 3 0. Okay, from this you can decide that 3 divides p square minus 1. Remember this one. Okay, now case 2. Case 2. We take this case. This is case 1. This is case 2. P mod 3 is 2. In this case, again I do the same step. I subtract minus 1. P minus 1. So 2 minus 1 is 1. So 3. It's according to the property. And plus 1. P plus 1 and 2 plus 1, it's 3 mod 3, and this can be written as 0 mod this, and based on this we know that P minus 1 P plus 1, I'm multiplying both of them, mod 1 multiply 0 3, okay, this 0 3. Okay, this means that 3 divides p square minus 1. Based on this case and this case, you can calculate that 3 divides p square minus 1. Whew, okay, that's it. Next. Here, I want to teach you Gauss theorem first. So if you have ABC, which is integer numbers, if A divides BC and A and B prime numbers, coprime numbers, coprime, A divides C, okay, because A doesn't divide B, so A must divide C. It's Gauss theorem. So we'll be using this in 5. Okay, let's start. So in 5 we have this: A divides C, B divides C, and A and B coprime numbers, and we gotta prove this one. Okay, now proof number 5. So we have A divides C. From this we can say that there exists K, which is integer number, of course. C equals Ka. A divides B means, what does it mean? There exists, let's say, K dash, which is integer. B equals K dash A. Not A. What? Oh, no, wait. It's not given, just forget this. Again, I tell you, I'm not making new video, I'm not gonna stop and pause, there is no editing. We are given this one. If we are given this one, there exists K dash this, and then C equals K dash B. Okay, because we are given this one and this one. And next, this is the first step. Number 2, I have C equals Ka, right? And now my goal is I want to prove that in this case B divides this K. I want to prove this one. Okay, so let's prove. I'm proving it here. So I have C equals Ka, right? I'm taking this one, and C equals this one as well, K dash B. And I also have A and B coprime numbers. So from here, like, look, from this I can decide that B divides Ka. Do you agree? And A and B coprime. And from here I can get B divides K. Why? Because of Gauss TH means theorem. Let me focus the video. Okay, so in here, because B divides Ka and A divides A and B coprime, B divides K according to Gauss theorem. And how do I get this one? I got this from here, and this is given from in the question first. And now what it means is B divides K means that there exists K dash dash, let's say, which is integer, k is equal to b times k dash dash, right? Then comma then we have c equals ka, and we have k equals b dash b k dash dash, right? A, which is ab times k dash dash. From this you can decide that c divides ab. Okay, that's it for number 5. Next page. Okay, next page. Oh, should I buy Ferrari or Lamborghini? I want you to comment. Ferrari or Lamborghini, which one? Next page, number 6. So we have 20, we need to prove 24 divides p squared minus 1, and p is this one. But based on number 2 and 4, we can have 8 divides this one and 3 divides p squared minus 1. So let me write it. 8 divides p squared minus 1 and 3 divides p squared minus 1. And I also know that 8 and 3 are coprime numbers. Based on this, you can have 8 multiplied 3 divides p squared minus 1. It means that 24 divides p squared minus 1. Whew, okay guys, that's it. I'll see you. Bye bye.